Throughout this practice, the necessary calculations were made for the preparation of the solution and not ingredients to be used in the laboratory, for which it was necessary to know the nature of the different reagents, the safety measures for the manipulation, and their supplies specification for each the culture methods prepared.
There are three types of solutions: unsaturated, saturated, and supersaturated. These are mainly differentiated by the amount of solid within them, according to the ability to dissolve a solid by the solvent. Once you have a solution, it's possible to calculate different types of concentration according to the way you want to refer the concentration: normality, molality, and percentages. Weight, weight volume, and volume volume. There are two techniques that are commonly used to verify the concentration in the solution. There are spectrophotometry and titration.
This practice methodology consisted mainly on developing correct calculations to prepare different solutions. The previous activity allowed us to determine specific characteristics and its possible dangers according to the globally harmonized system of classification and labeling of chemicals. Within this, personal protective equipment needed for safe use. Then the calculations were made, as you may see in the following results, where volumes and mass required for each solution were determined by the given concentrations from the protocol. Finally, each solution was prepared by a member of the laboratory group, whose responsibility was to prepare it according to the considerations previously indicated and investigated, such as pH adjustment, stir conditions, shaking, and heating.
This is a flow diagram which includes the general steps for the preparation of a solution. First, in a conical tube whose volume depends on the final volume of the solution, place 70% of water in the final volume. Then calculate the weight or volume of the reagents of the solution, taking into account the concentration at which they are found and the desired concentration. Then take the necessary quantity and as accurate as possible of each reagent according to the calculations. Add the reagent to the beaker or conical tube with water. If necessary, to homogenize, place the vessel in magnetic stirring on an electric grill or the tube in the vortex. If another reagent is required, add to the water and mix in the same way. If the solution requires a specific pH, check pH with the potentiometer and adjust to the desired pH. Once all of the reagents have been added and the pH is the right one, augment the solution to the final volume required. Then, pass the solution to an appropriate container according to its volume and characteristics. If necessary, sterilize, otherwise save the solution under the specified conditions. These were all the calculus that were made in order to prepare the solutions required. So let's explain how these were made. In solution number 1, a 1 molar glucose in 35 ml solution is required. The amount of glucose needed to prepare the solution was obtained from the values given and from some research. This data was substituted in the molarity formula, which establishes that the molar concentration is equal to the moles of solute among the liters of solution. In this case, we have the molarity, the molecular weight, and the liters of solution, so that the mass of the solute is cleared, and thus we obtain the amount in grams of glucose that is required for the preparation of said solution. This same procedure was used in the solutions 3, 4, 5, 6, 7, 9, 12, and 15. Now, for solution number 2, where a 70 milliliters of 50% glycerol solution is required, the volume was multiplied by the percentage established, with no need of units conversion. This simple procedure was also used in solutions 8, 10, and 13. Finally, for solution number 11, where a 9 milliliters of buffer TE is required, the dilution equation was employed for each component of the buffer. For trees, we have that the initial concentration was 1 molar, and the final concentration and volume are 0.01 molar and 9 milliliters respectively, so that the volume that must be taken from the stock solution is cleared. This same procedure was used for the preparation of 100 milliliters of stock medium. And the rest of the solutions were solved using a simple rule of 3. From the results of the calculations, we obtain the quantities of mass or volume that are required of reagents and solutes for the preparation of the solutions with which we will work in the following practices. In general, for the approach and resolution of the calculations, the formulas most used were the molarity and the dilution equation. On the other hand, the results were obtained in units of grams, milliliters, and microliters, the most commonly used to work in laboratories.
The most commonly used concentration measurements are those in which the amount of solute is compared with the final amount of solvent, among which are molarity, normality, molality, parts per million, percentage, and concentrated solution. The molarity presumes both the moles and volume depending on each compound. Using moles allows the easy change to mass for further calculations. Most solutions in the laboratory require molarity to ease calculations, such as buffers. The normality results very useful when working with acids and bases because it relates its equivalents working on the solution as mass over all the compound used. For sodium hydroxide solutions, for example, the molality, as well as the molarity, presumes the number of moles, but considering the solvent's total mass. The parts per million are useful when having very few parts of a component with respect to another. This could also be used as a percentage, and mainly it is used to avoid using a large amount of decimals and scientific notation. It is used, for example, in water dilutions and pollutants. The percentage of weight, by being dimensionless, allows it to work as a factor between different magnitudes. They are used when the solute is a solid, as in the loading buffer preparation. The percentage of volume, by being dimensionless, allows it to work as a factor between different magnitudes. It is used when the solute is a liquid, and its density is needed to make the calculations. Finally, the concentrated solutions reduce the amount of volume and time of preparation. Being more concentrated simplifies further preparations. This causes the stock solutions to be used in further solution preparation. When talking about solution preparation, here are 10 important aspects to consider in the procedure. Number 1. Work under sterile conditions and use molecular biology graded water if needed. Number 2. Verify if the material is clean enough to use it. Number 3. Know the nature of the reagents as well as its composition and special handling characteristics. Number 4. Wear nitrile gloves if needed. Number 5. Adjustment of pH while properly using the potentiometer. Number 6. Consider the total volume of the solution to avoid error in the measurements. Number 7. Work as precise as possible. Number 8. Know the future use of the solution in the laboratory in order to determine whether to sterilize it or not. Number 9. Calibrate the analytical balance to improve the accuracy of the measurements. And finally, number 10. Calibrate the potentiometer to improve the accuracy of the pH measurements in case one of the solutions needs a pH adjustment. Example number 2. Too much gel red in agarose gel. The dye gel red favors the visibility of the DNA bands along the gel after the electrophoresis. However, a big amount of dye can generate discrepant migration of the DNA. Example number 3. Incorrect preparation of 70% ethanol solution could interfere in the DNA extraction by adding contaminants while washing DNA pellets for purification.
Preparing solutions is a basic task while working on a laboratory. It involves the management of concentration concepts and theory, determination of certain characteristics of compounds used, and a correct methodology to apply when preparing any solution. The establishment of a correct workflow promotes the reduction of failures and sources of error at the laboratory. A crucial factor for this practice, where reliable calculations and precise preparations results in a well-prepared solution, which used in future practices reduces possible sources of contamination and undesirable results. It is important to consider that by knowing each substance's purpose, we can indirectly detect possible failures when interpreting future results as a feedback source.